The deep sea, which is really everything other than the continental shelves, accounts for maybe around 90% of the total ocean area. But we're only going to spend one lecture on it. It's perhaps a little unfair, but there's a lot more variation in coastal depositional environments. So this video covers the composition, the formation, and the preservation of biogenic or biologically produced sediments in the deep ocean. We'll focus primarily on the two main types of biogenic sediment, calcium carbonate and silica. So fine-grained calcium carbonate sediment, or calcareous ooze, covers nearly half of the ocean floor, including large areas of the Atlantic Ocean, the Indian Ocean, a little bit of the Pacific, especially in the southern or eastern Pacific. Calcareous ooze is composed primarily of the microscopic shells of single-celled organisms that live near the surface of the ocean. And when these organisms died, their shells sank to the seafloor and accumulated in the sediment. These shells are made of precipitated calcium carbonate formed by things like planktonic foraminifera and by coccolithophores. Both of these are single-celled organisms that make their shell from calcite. A few use aragonite, but not too many. Interestingly, both of these groups evolved in the Mesozoic, so there likely would have been little, or if any, deep-sea carbonate sediment, at least far away from the coastlines prior to that time. So unlike today, most carbonate in the Paleozoic, for example, would have been deposited in shallow coastal or what are called neritic environments. One specific type of carbonate sediment is chalk, which is this white rock here made pretty much exclusively from the shells of coccolithophores. Chalk is not restricted to the deep sea. It can form in continental shelf environments as well as in these Cretaceous deposits here at the famous White Cliffs of Dover. Incidentally, the Cretaceous gets its name from the abundant chalk deposits within it. So looking at this map here, you may notice how the Atlantic Ocean is nearly entirely covered with calcareous ooze, while the Pacific, especially the North Pacific, has much less. And in the South Pacific, the eastern side has a lot more calcareous ooze, and the central part has less. So in the next few slides, we're going to consider the factors that control accumulation of calcareous ooze. So carbonate sediment precipitates from calcium and carbonate ions in seawater. So its chemical equilibrium is governed by this solubility product KSP. So we can define a term called omega, which is just the ratio of the concentrations of calcium and carbonate ions divided by the solubility product KSP. Omega is called the saturation state. There's an omega or saturation state for calcite, and there's also one for aragonite, which is slightly different. Aragonite is slightly more soluble in seawater. An omega of less than 1 means that carbonate is undersaturated, and therefore it should dissolve back into calcium and carbonate ions. Omega greater than 1 is called supersaturation, and in this case, carbonate should precipitate from dissolved ions in the seawater, at least under equilibrium conditions. There can be kinetic barriers to precipitation. So, given this relationship that omega greater than 1 favors precipitation, you can probably tell that precipitation is more likely to occur when there is either greater calcium concentration and or greater carbonate concentration in the ocean. Saturation is also higher, and it's a lot easier to precipitate calcium carbonate in warmer water, for example in shallow tropical oceans, as well as at lower pressure, so in shallow water. The saturation state is primarily affected by the ion concentrations, but it turns out that calcium concentration is relatively constant throughout the oceans. Because the element has a long residence time. That means it's well mixed throughout the ocean. Therefore, it's carbonate ion concentration that's the main control, because it's more variable throughout the ocean, especially because of the effect that pH has on carbonate speciation, or the distribution of different carbonate compounds. The carbonate system is fairly complex. CO2, dissolved carbon dioxide, will dissolve into seawater to form carbonic acid, or H2CO3. And that then dissociates into bicarbonate ions and ultimately carbonate ions plus protons, or hydrogen ions. So adding CO2, for example, from decaying organic material into the deep ocean reduces the pH and tends to shift the balance of these equations, ultimately reducing the carbonate ion concentration, which is the black line in this graph, in favor of bicarbonate and carbonate. So as pH decreases, for example, when there's more CO2 in the water, the carbonate concentration goes down, and therefore calcium carbonate saturation, or omega, also decreases. So saturation state omega decreases with depth. This is especially because of the effects of decreasing pH, but also due to the effects of decreasing temperature in deeper waters and the effect of increasing pressure. So there is a depth in the ocean, typically around 4 to 5 kilometers today, where the carbonate ion concentration, the dashed red line in the graph here, becomes lower than the saturation state, which are the sort of vertical blue lines. At this line, at around 4.3 kilometers in this graph here, the carbonate concentration is less than the calcite saturation, and so omega is less than 1. And carbonate is what we call undersaturated. So this depth, or this layer position in the ocean, is called the lysocline. So even though carbonate should and does start to dissolve before the lysocline because it's undersaturated, it can still accumulate in the sediment there. So in this example diagram, it gives you sort of 4 scenarios. Starting on the right-hand side, sediment is supplied in a 9-to-1 ratio, 9 parts carbonate or calcite and 1 part something else. So above the lysocline, the sediment also has this 9-to-1 ratio. But below the lysocline, some of this carbonate burns off, a little squiggly line going back up into the water. So at the shallowest sublysocline depth, the second example from the right, there's still a 9-to-1 ratio being supplied from the surface, but 5 parts of that carbonate dissolves or burns off, leaving only a 4-to-1 ratio in the sediment. So the sediment is below the lysocline, but it still contains calcite. The 2 other examples show you sort of increasing dissolution below the lysocline. So basically, sediment can be preserved below the lysocline as long as the supply of carbonate exceeds the rate at which it dissolves. Once it makes it into the sediment, the carbonate that dissolves in there can help build up the carbonate ion concentration and the calcium concentration in the pore waters, and that eventually will limit further dissolution. But there is a depth below the lysocline where all the carbonate is finally dissolved and does not occur in the sediment. This depth is called the calcite compensation depth, the CCD. It's sometimes also called the carbonate compensation depth. It's the horizon, or the depth in the ocean, where the dissolution rate exceeds the sedimentation rate. And as a result, no calcite is actually preserved in the sediment. The CCD is always below the lysocline, and the difference between the lysocline and the CCD depends on the rate of sedimentation. You can kind of think of the CCD as like a snow line on a mountain, where the peaks of the mountain are covered by this white carbonate sediment snow, and the deeper parts lack this carbonate sediment, anywhere below the CCD. So the CCD is affected by all the factors that affect carbonate saturation. It's located around 3 to 5 kilometers depth in the modern ocean. I'll note there's also an aragonite compensation depth. It's a little bit shallower than the calcite compensation depth. So the other main type of biogenic sediment is siliceous ooze, also produced as skeletons of microscopic organisms, in this case things called diatoms and things called radiolarians. These organisms make tiny shells of something called opal A, which is an amorphous form of hydrated silica, or SiO2. Siliceous ooze doesn't cover very much of the modern ocean. You can see it's primarily restricted to the Southern Ocean, around Antarctica, some regions of the equatorial Pacific and Indian Ocean, and a little bit around the North Pacific up by Japan and Alaska. Siliceous ooze produced by radiolarians becomes something called radiolarian chert. I note that not all chert is produced by radiolarians, but chert is actually a pretty important rock type in sedimentary record, especially in accretionary prism type sediments like the Franciscan complex in California. Radiolarians have been around for a long time, since the Cambrian, and so you can find radiolarian chert in rocks of all sorts of Phanerozoic ages. Diatoms, in contrast, evolved much more recently. They really didn't become common until the Cretaceous. They produce, when they occur in enough numbers, a rock called diatomite, a fine-grained, very light, often white-colored sedimentary rock made of diatom shells. The Monterey Formation, which includes exposures around Santa Cruz, the Santa Cruz mudstone, contains a lot of pure diatomite, which is mined for economic reasons in many places, or diatomaceous mudstone in some regions, like the Santa Cruz mudstone. So silica is highly undersaturated in the surface ocean. The upper figure on the right there, silica concentrations are basically zero in most regions. It's a little bit higher around Antarctica, the green and reddish colors. The concentration of silica is so low in the surface ocean because it acts as a nutrient element. Radiolarians and diatoms just suck it up so rapidly that they completely deplete the surface ocean concentrations of silica. Like other nutrient elements, silica is more concentrated in the deep ocean, although it's still undersaturated there, and there's also a lot of interocean variation. The lower map shows silica concentrations at 1,000 meters depth. You can see there how it's still pretty low in the Atlantic, especially the North Atlantic, but it's increasing towards higher levels in the Pacific and especially the North Pacific. So the question is, if silica is undersaturated everywhere, even in the deep ocean, how do we get siliceous sediments preserved? Well, the main reason that silica is preserved is that it is found in areas where the flux to the sediment, the rate at which silica sinks to the bottom, is extremely high. The preservation of silica, even though it's undersaturated, is analogous to the lysocline and the CCD for carbonates. So if you remember, calcium carbonate can be preserved in the sediment below the lysocline. The lysocline is where it's undersaturated. So even though the bottom water is undersaturated, you can still preserve calcium carbonate above the CCD at least, as long as the sedimentation exceeds the dissolution. So the same thing applies for silica. The oceans are undersaturated everywhere, yet silica can be preserved in the sediment where it is produced at very high rates. And so there's actually a very strong correspondence between the map here showing high silica production in the Southern Ocean, the Equatorial Pacific, the North Pacific, and regions where there's high silica in the sediment. High production in the North Atlantic doesn't really correspond to a siliceous ooze deposit in the sediment, I think because silica saturation is even lower there, and because carbonate sedimentation is also kind of high there. It's also possible that these siliceous microfossils may be covered by an organic coating which protects their shells, or their frustules as they're called, from dissolution even after they die. So for the silica, as well as I guess for the calcite below the lysocline but above the CCD, it's kind of like, you can imagine that many of these diatom shells are dissolving and giving their life so that the other ones can survive and be preserved in the sediment. The needs of the many outweigh the needs of the few. So the final major type of deep sea sediment is actually not biogenic at all. It's called abyssal red clay or deep sea red clay. It dominates in regions where calcareous and siliceous sediments are absent. For example, the Pacific, especially the North Pacific, is kind of the main region you can see of abyssal clay. There are little blobs here and there, but the Pacific is really the main area of it. Red clay has varied sources. Some of it actually comes from space dust, so some of the red clay is meteorite fragments and meteorite dust, but primarily comes from wind-blown dust from the continents. Giant dust storms in desert regions, like in the Sahara, can send dust all the way across ocean basins. I mean, Sahara dust has been found in lakes in North and South America even. So these deep-sea red clays, they're basically the default sedimentation. Dust accumulates everywhere, but at pretty slow rates. So because it's deposited really slowly, it can be swamped out and just overwhelmed by calcareous or by siliceous sediments where they form, since they're accumulating much, much more rapidly. So any dust that does accumulate makes up a small fraction of the sediment and is primarily calcareous or siliceous ooze. Basically, red clays dominate in places where biogenic sediments aren't found. So, for example, at deeper depths, like below the CCD, as well as in mid or high latitude regions away from the high productivity diatom or radiolarian bloom areas.
Water with a lot of dirt or sediment floating in it has a high turbidity. Microorganisms that can make us sick, known as pathogens, cling to the dirt in turbid water. Separating water from dirt is a process called sedimentation. It is an effective way to remove some of the pathogens contaminating our water, so that it is safer to drink.